This is the knowledge extraction analytics component, for short KEA, of the Threat Intelligence Engine layer of the CUREX platform. The KEA component harvests knowledge out of system subcomponents and network communication interfaces that deal with health data sources in order to construct models and design methods capable of detecting threat patterns. In this slide, we briefly present the scope of Task 3.2 in which KEA is developed. The implemented solution satisfies all the specified requirements. The KEA component is implemented and integrated in the CUREX platform, offering threat detection and threat profile identification functionalities based on complex event processing and machine learning. KEA complements the main functionality of the TA layer, providing online threat prediction and monitoring functionalities. It also provides an interface to assist the research around CVEs, CWEs, and CAPEX as it will be presented. KEA can be deployed either as a standalone tool or as an embedded component inside the CUREX platform. The figure presents the embedded deployment architecture, which is the focus of the demonstration. As it is presented in the figure, the analytics mechanism of the KEA component consists of three main subcomponents: the complex event processing-based threat detection, for short CEPTD, the machine learning-based threat detection, for short MLTD, and the outlier detection, for short OD. There are also other subcomponents to support the functionality of the main ones. The controller subcomponent provides both a graphical interface for the security experts and an API endpoint for the components of the CUREX platform that communicate with KEA. Controller also acts as a central hub for the distribution of the information of the other subcomponents. The CAPEX manipulation subcomponent, which works on par with CEPTD and provides recommendations regarding CAPEX, CVEs, CWEs that might interest the security expert. The event generation subcomponent, which can be used in the standalone deployment of the KEA to assist the MLTD functionality. And finally, threat reporting, which is responsible for the visualization and the distribution of the results of the KEA analytics subcomponent. KEA is accessible through an API and a web interface. We can access its graphical user interface through a web browser. Authentication is used in both the graphical interface and the API endpoints of the component. The home page offers a dashboard functionality which acts as the command center of KEA. In the dashboard, we can stop all the three main subcomponents, or we can also apply some specific queries. We begin the demonstration with the MLTD component. For the MLTD component to work, training is needed. MLTD is trained on timestamp annotated events obtained from three sources: the TA layer, and more specifically from the deployed CM tool, the asset and vulnerability discovery layer, and more specifically by security experts or admins that report important security incidents, and optionally the output of the outlier detection subcomponent. For demonstration purposes, we emulated some traffic in January of 2020, so we have the XLCM table filled with hypothetically reported security events from the TA layer, and the ADT table filled with hypothetically reported important security incidents. If we zoom into the diagrams, we will observe that after every sequence of reported events from XLCM, there is a reported incident from a security expert or system admin in the ADT diagram. Of course, this absolute alignment is just for the sake of demonstration. Now that we have created our artificial dataset, we are ready to start the MLTD service and train our model on those generated data. So we go on the dashboard, and from the MLTD we start a new instance. As we can see here, a new instance is running and we can stop it from here. The training functionality is not offered through the graphical interface. For that purpose, we used Postman to trigger the training, providing the required information. As we can see here, the training process is started. Let's wait until the training finishes. Training is finished. As soon as the training is finished, we can obtain the newly identified threat patterns. This information is also accessible from the Asset and Vulnerability Discovery layer in order to assist the identification of new CAPEX CVEs and CWEs. In the MLTD section of the dashboard, the security expert provides the number of the top identified event IDs that she wants to obtain. These event IDs are preceded to the trained type of attack. The top events of the list are the most important ones and compose a pattern of events that occur before the trained attack. MLTD returns the IDs and a specified time frame which defines a time range in which the returned events are expected to occur in order to pose a threat. For demonstration purposes, we use an artificial dataset of male names. Apart from the threat pattern identification, MLTD offers an online functionality which monitors the obtained events from the tier layer at runtime and reports if there is any predicted threat. For the demonstration of this functionality, again we produce artificial traffic. As soon as a threat is detected, as we see here, it is visualized in the MLTD page. This report can be forwarded back to the tier layer for further assessment. We continue with the presentation of the outlier detection subcomponent functionality. We start a new instance using the dashboard. In the demonstration, we are monitoring pickup files for TCP packet losses. If there is any sudden increase in the number of packet losses, a report is generated as it might be an indication of distributed denial of service attack. Using the dashboard, we upload a pickup file. Normally, this file is sent to the KEA component through a POST request to the controller and then is directly pushed to the outlier detection subcomponent. However, we also offer this functionality through the dashboard to assist the security expert in their research for security flaws. Analyzing the uploaded file, a report is generated and visualized in the OD page. Finally, we present the SEPTD subcomponent, which is only used in the autonomous deployment of the KEA component and not in the embedded one, as its functionality is already offered in the tier layer inside the CUREX platform. In the presented scenario, we monitor a local network interface for possible malicious activities. In our example, we will show an SQL injection attempt on the WordPress platform and demonstrate how SEPTD provides further details on the related CV, CWEs and CAPEX for a specific attack. In the demonstration, SEPTD is already running. We can monitor various metrics using the SEPTD page. Kibana, with a pre-specified set of diagrams, is incorporated in the GUI. Some representative diagrams are an event histogram which encapsulates monitor events, unique IPs and SSL client fingerprints in the network traffic, an alert category histogram in which suricata alerts are categorized based on their threat levels, and other helping diagrams. Using an external device, we emulate an attack to the monitor interface in order to trigger the appropriate rules of the suricata tool. As soon as an attack is detected, we can see it in Kibana on the suricata alert signature top 10 and suricata CVE top 10 diagrams. By clicking the respective record, we can get further details of the attack provided by the cvedetails.com database. In the dashboard, using the CAPEX manipulation subcomponent, the security expert can navigate through the relations of the detected CVE to CWEs and CAPEX in order to assist the new rule generation process. For example, a possible interpretation of the output record is that an SQL injection attack targeting the WordPress platform was detected by suricata based on Rule 244.08, which corresponds to CVE 2007-1409. Furthermore, by examining the connection of this CVE to CWEs, we can create a possible end-to-end mapping to CAPEX 21. This kind of mapping may assist the security expert to further deduce new suricata rules. The presented tool is context agnostic as its data analytic mechanisms are generic. It combines information between multiple layers of the CUREX architecture and offers an ensemble security monitoring solution that assists the new threat pattern identification and the exploration of new CVEs and CAPEX. The implementation of KEA is in accordance with the description of actions as it persists logs, it takes into consideration publicly available security data lakes, it conforms to the requirements specified in Task 2.1, it offers techniques for revealing vulnerabilities and profiling threat patterns using machine learning and data analytic techniques, and finally, it utilizes historical data in order to train machine learning models for threat prediction and threat profiling, offering an agile refinement methodology. Thank you for watching.